we got? Liquid water breaks down into hydrogen and oxygen if you put enough heat into it, or electric current. In the reaction represented above, the molar enthalpy of decomposition of H2O is, okay, this is the delta H for this reaction as it's written. But this reaction assumes that you're starting with 2 moles of water and getting 571.6 kilojoules. If you're doing the delta H for water in kilojoules per mole, there's an important step you have to do, and that is 571.6 kilojoules is for 2 moles of H2O. 571.6 divided by 2 is 285.8. Sorry, not enough room. 285.8 kilojoules per mole of water. This is important to catch. It happens a lot. It's like, this would be like saying I bought 2 shoes for $57. And then they say, so how much did you pay for per shoe? It's very natural to go to this number, but you would like, well, wait, that $57 was spread out over 2 shoes. So technically I paid $28.50 per shoe. That's what's happening here. The reaction is saying, if you started with 2 moles of water, you'll get this much energy. We're saying, or you'll have to put in this much energy. We're saying, well, I'm only interested in half that much water, 1 mole. So I guess I only need half that much energy. So our delta H is the 285.8. A and B are traps. And now what's the second bit? If the enthalpy change were included as a term in the reaction, it would be a... So if we wrote this delta H in line instead of as a delta H, where would we put it? It's positive, which means the reaction is endothermic, which means heat is something else we have to put in. If we wrote this, we would write it on the left-hand side. 571.6. We'd say this reaction requires water and also requires heat. You have to provide that or the reaction won't go. So the heat is another reactant. And so we're liking that one. Keep an eye out for this, by the way, when you're doing the online exams. Most of the online exams are set to shuffle the multiple choice answers, which is good because it keeps the test from looking the same every time. But it also means like that things that you would think would be in alphabetical order are not. If you're doing the question like this and you get row C, you have to go, okay, that's row C. The answer is actually A, and this is the button you click. That's fairly straightforward, but if you're in the middle of a test and a little nervous, this is the kind of thing you might miss, and that's a crummy way to miss a question. So please watch out. Okay, a hand warmer packet contains a mixture of powdered iron, carbon, sodium chloride, sawdust, zeolite, all moistened in a little water. The packet is activated by removing the plastic cover, which exposes the materials to air, and the reaction that occurs is iron. The powdered iron reacts with oxygen and air, produces iron oxide. So basically the iron rusts at high speed and throws out a fair bit of energy as it does, and that's how those hand warmer packs work. And they say if there's 2.5 grams of iron oxide produced, then the energy transferred is how much? Well, the energy transferred by any chemical thing is E equals N delta H. And we want the total energy, so we're trying to find this. We need the number of moles of iron oxide, which they didn't give us, but we can find it. So, sorry, side calculation. The number of moles of iron is its mass divided by its molar mass. The mass is 2.5 grams. The molar mass for Fe2O3 would be, well, iron is 5585 times 2. Oxygens are 16 each, and we have 3 of them, so that's 48. I get 159.7 for the molar mass of iron 3 oxide. So 2.5 divided by 159.7 equals not very much. We get 0.01565 moles of Fe2O3. That's our number of moles down here. 0.01565. And the delta H is 1648.4, right? Hope you said no. What do we have to fix about this? This 1648.4 is for 2 moles of iron oxide, which we do not have. For 1 mole of iron oxide, imagine cutting everything in this reaction in half. If you had 1 mole of iron oxide, you'd only have half this much energy, so you would have 824.2. 824.2 kilojoules per mole. So whenever you're doing the delta H for one of these, remember, don't just automatically trust this number. It should be this number divided by a coefficient. If you're lucky, that coefficient's 1, and it's not, the number will not change. But in the last couple examples, it hasn't been a 1, and we've had to do a tweak. We've had to say, well, this reaction is 2 times too big, so I'm going to say I only want half this much iron oxide. I'm only getting half this much energy. So when we finish that, 0.01565 times 824.2, I get 3 digits, so 12.9, they say. And that makes sense. We would have done 3 anyway because 3 sig digs in that data. So 12.9 kilojoules. The energy transferred is 12.9. Transferred makes me think they don't care about the sign on this. And also it's hard to say if you should put a positive or a negative on this because it's being released by the reaction and absorbed by the water, so which one do you emphasize? So most likely they'll be happy as long as you say 12.9. Okay, written response again. Use the reactions below to calculate the molar enthalpy of formation for cetane. The molar enthalpy of formation. Okay, I'm not sure we're going to need all of these, really. I think we only need this, because this is the only one that talks about cetane. I think we have one reaction here that's critically important and 2 others that we don't need at all. So let's clear a little space and hack our way through this. This is an application of Hess's law where we do products minus reactants to find the delta H for something. And I am going to say I am reasonably sure we don't need reactions 2 or 3. All we care about is this because this one has cetane in it. If you were to find the delta H for this reaction, I know it's right here, but pretend you don't see that. If you were going to find this delta H, how would you do it? You'd do the heats of formation of the products minus the heats of formation of all the reactants, and that would equal the delta H for the reaction. If we get into that in more detail, the products would be 32 times minus 393.5, that's carbon dioxide, plus 34 times, that's liquid water, so minus 285.8 is the heat of formation for water, liquid water, minus, on the reactant side, we have 2 times, I was going to use C for cetane, but that'll look like carbon, which might be a little weird. I'll just do kind of an algebra style X. This is the heat of formation for cetane. It is not in our data book. We have to find it somehow, and right now we don't know it. So 2 times an unknown X for cetane plus 49 times, what's the heat of formation for oxygen? 0, because oxygen just comes that way. Most of the oxygen in the universe is already O2, so Its heat of formation is zilch. You don't have to pay any energy to make O2. That's just how you find it. So this is products minus reactants, and this comes out to our delta H, and somebody already did this, and they're telling us the answer is minus 21,672. So we know everything about this reaction except for this X, which means we should be able to solve for it. So let's do some math and see what comes out. 32 times 393.5 is minus 12592. 2592 plus. And for the water, we get 34 times 285.8. This is negative 9717.2 minus, and then here we get 2x, and that's it. 49 times 0 isn't worth keeping, equals minus 21,672. We can add these together. 12592 plus the thing I already had, minus 22,309.2 minus 2x equals minus 21672. I'm not sure these brackets need to be here anymore since there's nothing outside them. So we just have that, and now this is math class. It's solved for x. I want to get rid of this minus 22,000 thing, so I'm going to add that on each side. Plus 22309.2 plus 22309.2. These cancel completely, and we get minus 2x equals minus 2x is 637.2. Divide by negative 2. And we get x, the heat of formation for cetane, must be minus 318.6. And that would be kilojoules per mole is the proper unit for a delta H. Fair enough. So you can use delta H when you, or sorry, you can use Hess's law when you don't know a delta H and you want to find it. You can also use delta H, I keep doing that. You can also use Hess's law in a reaction where you know the delta H, but you don't know one of the heats of formation. You can work backwards and find it by writing out this entire expression and then doing some algebra. Okay. This is an energy graph, or energy diagram, and it's showing us that we have a reaction that starts with some chemicals over here, and it ends with different chemicals over here. And normally, to make that reaction go, you have to put in energy to get up to 0.3, and then the rock rolls downhill, so to speak, and the reaction goes by itself until you get to the end. But a catalyst is a helper that makes a reaction go easier, and in this case they're saying there's a catalyst that gives us this curve instead, which means you don't have to put in as much energy. Instead of getting to the top of this hump here, you only have to get to the top of this lower hump, and then the reaction goes by itself and you end up in the same place. So 3 is the normal reaction, 2 is the catalyzed reaction. And if you had to find the energy for it, if you had to find how high that bump is, it would be energy 2 minus energy 1. Like for instance, if this was 600 and this was 150, and you wanted to know how far apart they are, you'd go 600 minus 150, and that would tell you that this is a 450 kilojoule jump. It's always the high energy minus the lower energy. Will give you the size of the delta H. So in this case, it's 2 minus 1. Okay, when methane gas is burned in a fireplace, the reaction that occurs is, here's methane. Sorry, methane is CH4, my bad. CH4 burns, it reacts with oxygen in the air, produces carbon dioxide and steam. Now, if you know anything about natural gas, you know that when it burns, it releases energy, but let's pretend that we've never heard of methane before and power through this. I'll try to go fast. This is the reaction. If we balance it, we need one carbon, two hydrogen there. Now we have four oxygen on the right, so we need a 2 there. And that means our delta H is products minus reactants, so it's carbon dioxide and 2 steam minus, and for reactants we have just methane, which is minus 74.6. And so delta H for this is 393.5 negative plus 241.8 negative times 2, and then minus negative 74.6 is like plus 74.6. So I get minus 802.5, if I'm not mistaken, kilojoules per mole. So even if you had no idea about methane, you can always write out the reaction and do this crunch yourself, products minus reactants, and find out if it's endo or exothermic. Now we know that this reaction is exothermic, which means we can junk 2 of our answers. And the original source of the energy stored in methane gas is, essentially methane gas is dead dinosaurs. It comes from decomposed organic material that's been compressed underground for a long time. That material used to be living material, which got its energy from photosynthesis, and that energy came from the sun. So except for a few things like geothermal energy that comes from radioactive decay, pretty much all the energy that you find on Earth originally came from the sun. Okay, what have we got now? They give us a bunch of reactions. They give us a potential energy diagram. The equation so normally I try to read through these and just kind of understand what's going on before I get to the question, but in this case, this is just an energy or an information dump, and I don't know what they want me to do with it. I need some guidance from the question. The equation that represents reactions that release energy to the surroundings. Okay, well, if a reaction releases energy to the surroundings, that means it starts out at high energy, and then you get a drop, and it goes to low energy. Reactions like that are exothermic, which means their delta H is negative. So this question boils down to, which of the following reactions are exothermic? Well, this one has energy on its reactant side, as in give me energy and then I'll do this. So that's endothermic. We won't be taking that one. This one says, take these chemicals, mix them in a bowl, and they'll react and they'll give you some energy. Energy is one of the things this reaction makes. So yeah, 2 is exothermic. 3 doesn't have the energy in line, but it does have a negative delta H, which is exothermic, so that's a yeah. And 4 has a positive delta H, which means it's endothermic, meaning nope, not what we're looking for. So 2 and 3 is looking good. Aerospace engineers are interested in using hydrogen gas as a fuel because of its low density. Hydrogen can be produced by the reaction represented by blah, blah, blah. Okay, so one way to make hydrogen is get methane out of the ground as natural gas, react it with steam with the help of a catalyst, and you'll get carbon dioxide and hydrogen. Seems like there might be better ways that don't produce carbon dioxide, but anyway, this is a valid way of making hydrogen, so let's go on. The enthalpy change for the reaction above is, I don't know, let's find it. The delta H for anything is products minus reactants. The products here are carbon dioxide, one of them, and hydrogen, which is a zero because it's a pure element. On our reactant side, we have methane, which we've seen already is minus 74.6. I had to look it up. I knew we'd seen it, but I didn't remember it. And we have two water in gas states, so 2 times minus 241.8. I know I'm right on the edge of the screen, sorry. I hope you can make that out. So, negative 393.5. Let's see, that'll be... I'm doing the signs on the fly in my calculator, which is why I'm kind of being quiet about the numbers I'm putting in. But if you do products minus reactants, I think we will end up in the same place. I get 164.7. Positive 164.7 kilojoules for the reaction represented by the equation above. So yeah, our delta H is plus 164.7. So I think we can lose C and D there. And the second piece is the enthalpy change per mole of hydrogen. Well, this reaction makes 4 moles of hydrogen. So if we want the delta H per mole of hydrogen, we'd have to do 164.7 kilojoules spread out over 4 moles of hydrogen, which comes out to 41.175 kilojoules per mole. And how many sig digs would we have for that? I guess this had 4 significant digits. This is a whole number. It's considered to have infinity significant digits. So technically this should round to 4 sig digs, but the best answer they give us is 41.2 kilojoules per mole. So I believe we have to go with that. If you're looking at this and thinking this has 3 significant digits and that's why the answer should have 3, the rules are different when you add and subtract. I can tell you all about that if you're curious. You can email the instructor and find out more. But when you're multiplying by a 3 sig dig number, that pulls your answer down to 3 sig digs. But when you're adding numbers like this, the fact that this has 1 decimal place is actually what matters. So sorry if that feels like moving the goalposts, but it is true. This answer, I believe, should have come out with 4 significant digits. But this is good enough for multiple choice. Clearly, that's clearly the best answer. None of the others are even close, so I feel okay taking B. And now, the ozone layer reduces ultraviolet. In the upper atmosphere, ozone is depleted by a 2-step reaction. Okay, so ozone is a funny form of oxygen with 3 atoms in it. It's O3. There it is, it's a gas. It can react with nitrogen monoxide, and when that happens, we get NO2, and the oxygen gets stripped down to, ozone gets stripped down to plain old oxygen. And then there's another reaction where the NO2 reacts with a lone oxygen atom. We get back our NO and a plain old oxygen. If you add these together, if you take reaction 1 and 2 and add them together, the NOs cancel out. The NO2s cancel out. And so your net reaction is just an ozone goes in, an NO2 goes in, and on the other side you get a couple of regular oxygen molecules. So, oh, sorry, that should cross out. Is there a typo in that thing? Let me look at that again. I feel like that's not adding up the way that they're saying. We start with an O3, and there it is. We use up an oxygen atom. There it is. We finish with 2 oxygens. There they are. The NOs cancel out. The NO2s cancel out. No, we're okay. I think I didn't cross out something I should have the first time. Okay, so the reaction makes sense, and it says ozone can react with oxygen atoms and convert to plain old oxygen molecules. So you can lose ozone this way. And they say this first reaction has, well, they're asking about the energy transfer, meaning the delta H's, and they give us the delta H's, but very indirectly here. For the first reaction, they say we start at 234 kilojoules, we fall down to 33.2 kilojoules. How much of a difference is that? If you do the high energy minus the low energy, 234 minus 33.2, you get 200.8. And it's negative because the energy drops. So equation 1 has a delta H of minus 200.8 kilojoules per mole. There's not really any way we could have looked that up, but you can get it from here because you know it's the distance between your reactants and your products. We could do the same thing for reaction 2 because they've given us those numbers again. To get from there to there, we're going from 282.4 down to 91.3. If you subtract those, 282.4, take away 91.3, we get 191.1. Negative again because the energy drops. Minus 191.1. Now, another thing you saw working with Hess's law is that if you have 2 reactions and you add them together, you can do that, but you must add their delta H's together. So add these up and we get 8 plus 1 is 9, 0 plus 1 is 1, 0 plus 9 is 9, 2 plus 1 is 3. They're both negative, good thing, or I shouldn't be adding them. And so our delta H is minus 391.9 kilojoules. Again, here they say energy transferred, which is kind of a way of waving off the sign, saying we don't care if it's absorbed or released, just tell us the amount. And the amount should be 391.9 kilojoules.